So up to this point, what we have discussed was actually deterministic finite automata. And actually what describes a deterministic finite automaton is that each of its transitions is uniquely determined by the current state and the input symbol. And reading an input symbol is required for each state transition. So you need an input to push the system to a transition. If you relax these two constraints, what you obtain is what we call a non-deterministic finite automaton. So what does it mean to relax these two conditions? The first condition says that the transition is uniquely determined by the current state and the input symbol. If you relax this, this means by the same current state input symbol pair, you can actually go to different states in each run. For instance, you are in one state, let's say with an input 0, you go to this state, but with another run with 0, you can go to another state. So this behavior is what we call non-deterministic finite automaton, because you do not exactly know in which state you will end up after the application of this input symbol. And the next one, reading an input symbol is required for a transition. And this means for non-deterministic finite automata, it's possible for the machine to make a transition from one state to another without an input symbol. So these transitions we call lambda transitions. So from a state, a transition without an input symbol or simply with lambda is possible. So no input symbol is applied. That means essentially that we can represent this by an application of lambda, the empty string. You have a state transition. Okay, so essentially two properties set non-deterministic finite automata apart from the deterministic counterpart. One, from a state, a transition to multiple states is possible with the same input symbol. Multiple in the sense that in one execution, maybe you transit to one of those states, but in another execution, you might transit to another one. And you also have transitions with lambda. Now, since these are defined by just relaxing these constraints and the other properties are the same, in a general sense, every deterministic finite automaton is also a non-deterministic finite automaton, just a special one. But in some discussions, non-deterministic finite automaton are specifically referred to those that are strictly not deterministic. And for some languages, designing non-deterministic finite automata might be easier than designing the deterministic finite automaton to recognize that language. But this is not a problem. This is not to bring a new set of automata into the picture, because for every non-deterministic finite automaton, there is an equivalent deterministic finite automaton that can be found through what we call the power set construction. I'm not going to give the details, but essentially you need to understand that given any non-deterministic finite automaton, there is an algorithm or there is a method that transforms it to an equivalent deterministic finite automaton that does the same thing, essentially, that is, and that recognizes the same language. On the other hand, non-deterministic finite automata are usually easier in certain cases than designing the discrete counterpart, because with the discrete one, you need to have all possible transitions. What happens when you are in this state and a 1 is input? What happens when you are in this state and a 0 is input? With non-deterministic setting, you don't need to put every possible transition. You can eliminate some of the transitions, in which case the language will not, or the input string will not be recognized. And you can have multiple transitions so that you can actually model let's say, an OR function. Okay, this is recognized or this is recognized. So with two different inputs, you can like branch out your state transition to recognize those two different inputs. So here are some examples. Non-deterministic finite automaton that recognizes the set of all bit strings with an even number of zeros or an even number of ones. To do this with a deterministic finite automaton, you need to keep track of the number of zeros and number of ones. So you need to be aware of all the possible cases, like even number of zeros and even number of ones, even number of zeros, odd number of ones, even odd number of zeros, even number of ones, odd number of zeros, odd number of ones. So you need to also fill out all possible transitions. It's going to be a large automaton. On the other hand, here you can simply separate it into these two finite state machines. One checks the even number of zeros and the other checks the even number of ones. Here you see with lambdas, I transit into one of those. And well, I have a mistake here in selecting the accepting states, because you see with an empty string, I'm at S3. So S3 acts as the counter for, or the initial state for counting the number of ones. So since I need an even number, S3 is accepting, because if you have zero ones, it should be accepted. But S4, it should be a non-accepting state, because S4 signifies you have an odd number of ones. And in this part of the non-deterministic finite automaton, you see the number of zeros don't play a role. It just keeps you in the same state. But in the half machine on the top, it's the other way around. And here S1 should be the accepting state. Again, this should be rectified in the slides because it signifies the case where you have an even number of zeros. Okay, so 0 here and 0 back takes you to S1. And S2 should be non-accepting. Okay, so you should see that you can actually come up with an equivalent deterministic finite automaton that does the exact same thing. Another example is that the non-deterministic finite automaton that recognizes the set of all bit strings starting with 0 or 1, 1. For instance, with from the initial state S0, with a 0, I go to my accepting state. And with a 1 and another 1, I also go to my initial accepting state, in which I stay with any further input. But you see, the behavior of the finite state machine in state S1, when an input of 0 is applied, is not defined here. Okay, so in that case, we will say that the string causing that is not going to be accepted simply. So this, you see, reduces the complexity of the finite state automaton, and therefore non-deterministic finite automata are sometimes preferred in studying such languages.